Let us then first start talking about galaxy morphology. And in any science, empirical science, when you begin, you don't know what you're looking at. The natural approach is to first try to classify things and order them in some way in their measured or observed properties. And so that happened with galaxies as well. But first, let me define galaxies are really the basic building blocks of the universe at large. And the interesting thing is they're not all the same. They have a very broad range of different physical properties in terms of mass and luminosity and star formation rate and what have you. And whatever we observe today is clearly a product of billions of years of galaxy evolution till the present day. So a big goal of cosmology or extragalactic astronomy is to indeed understand how did galaxies form, how did they evolve, and got to be the way they are today. So in rough numbers, within our observable universe, which is how far we can see since the Big Bang started, there is of the order of 100 billion galaxies. Probably more if you count some dwarfs. And on average, they each have like 100 billion stars. Their masses range from 100 million solar mass for things like dwarf galaxies to 10 to the 12, even 10 to the 13 solar masses for really big ones. And as you can see, that there really is a very broad range of properties. So indeed, just like biology really began with Linnaean classification of living creatures, so did extragalactic astronomy. Hubble first proposed his eponymous classification in a popular book called The Realm of the Nebulae, because even then they were still calling them nebulae because concept of galaxy as island universe was still relatively recent, even though Hubble was the one who actually proved that that's the case. And then others have tried to improve on it, but there hasn't been any major change. And we still use Hubble's classification, even though it's not a perfect one, and I'll talk about that in a moment. Now, a better, more quantitative way to do this is to actually measure stuff and look how different physical properties group together or separate or correlate and objectively define sets of galaxies as belonging to same families of objects. But then we can also look at building blocks of galaxies like those that we talked about last time in terms of stellar populations, bulge, disk, and so on. So anyway, here is Hubble's famous classification, like tuning fork diagram as they call it. And it begins with elliptical galaxies and then goes to spirals, which he split into two different branches, those with central bar and those without. He ordered ellipticals in their apparent ellipticity on the sky, which clearly is subject to projection effects, and now we know, in fact, doesn't really matter very much for any other physical property of ellipticals, but that was the visible thing. Spirals he sorted in sort of degree in which spiral arms were prominent, and that also corresponds into the relative importance of bulge in disk. You can think of bulge as a little elliptical in the middle of a spiral. And Hubble thought that this was an evolutionary sequence that goes from left to right, and he called the ellipticals early type galaxies and spirals late type galaxies. And now we know that this actually has nothing to do with reality, and galaxies don't evolve this way. If anything, you can mirror flip this image and merge two spirals to make an elliptical, but that's a different story. So elliptical galaxies. Here is a nice prototype. Actually, it's an unusually big one. It's M87, biggest galaxy in the Virgo cluster. And it exemplifies many of the properties of big ellipticals. You can notice that there isn't any structure to speak of. All these things that you see on top of the M87 are just foreground or background galaxies. So there are no spiral arms, there is no obvious star formation, and so in fact Hubble kind of defined them that ellipticals would not have any star formation or spiral arms and things like that. He was actually incorrect in terms of star formation. There can be some star formation in ellipticals, but that's a more recent development. So they're very smooth, symmetric, as the name implies, they are elliptical. Here are two other big ellipticals in Virgo cluster. And they don't have much cold gas unless they have just accreted some. However, they're not gas poor. There is plenty of gas in elliptical galaxies, except it's heated to millions of degrees of Kelvin. It's an X-ray gas, and a hot gas like that cannot be converted easily into stars, because stars require formation from cold interstellar medium. Now, ellipticals are largely made out of old but metal-rich stars. You may remember that Bade's original idea was that population 1 stars, those like in disk, chemically evolved, metal-rich, and population 2 will be the old stars. These are old, but they're not metal poor. They actually underwent substantial amount of evolution. And another important thing is that ellipticals tend to like dense environments, clusters of galaxies, cores of clusters, and things like that. Spiral galaxies, well, we covered that at some level when we spoke about Milky Way and spiral structure. That is the defining characteristic. And there is actually an interesting correspondence between Hubble types and real properties of galaxies. So there are these two sequences that are in parallel, one with bars, one without. As you go from the earliest type, where bulge is dominant, the least developed spiral arms, to the other end of the sequence, where bulges are essentially non-existent, there is the spiral arms are very prominent. There's a lot of star formation. There is clearly some sort of gradation in meaningful physical properties. But at any given Hubble type, there is a huge range in masses and luminosities and so on. So many of the very important physical properties of these objects are not correlated with Hubble types. This is a textbook example of a barred spiral. There is a bulge, there is elliptical bar. From the end of the bar begin spiral arms. And roughly about a half of all spiral galaxies have bars, including our own. And they can be very luminous parts, maybe up to a third of all starlight. As we already discussed, they're dynamically distinct systems. They rotate like a solid body rotation. And whether or not galaxy has a bar depends on the exact balance between gravity of the dark halo and the self-gravity of the disk. So spirals are just like on the margin of that. And they're not density waves. They're a completely different dynamical thing. There is the intermediate type, so-called lenticular or S0, before SA galaxies. And those are disk galaxies without spiral arms. Now, this is maybe the most famous one. It's called Sombrero Galaxy. And as you can see, it does have dust and actually has some star formation in there. But it's a gigantic bulge and no spiral arms. By and large, these galaxies, former disk galaxies, spiral galaxies that have lost their gas somehow. Maybe they just burned through all of it, but more likely the gas is swept as they move through, say, clusters of galaxies, and then that extinguishes star formation. The ultimate end of Hubble sequence are so-called irregulars, and Magellanic clouds are local good examples. This is the Large Magellanic Cloud. It turns out actually it's not a great example of what dwarf galaxy is. This is a small spiral that is being eaten up by Milky Way. And what's left here is probably remains of its own bar, but there's plenty of star formation. Not all dwarf galaxies make stars of gas. In fact, majority don't. And they've been called dwarf ellipticals or dwarf spheroidals, and they're neither elliptical nor spheroidal. The example of the so-called dwarf elliptical is one of the Andromeda satellites, NGC 205. You can see that it's got a little tiny nucleus in the middle. It's old stars, mostly supported by random motions. And dwarf spheroidals are these collections of stars that seem to be actually, well, they are embedded in halos of dark matter, but there isn't much light left. There are many of those. Milky Way has a couple tens of satellites like these that we have found so far, and so do other galaxies as well. We think that these are the original building blocks of galaxies, that when galaxy formation begins, it starts first in smaller pieces, like the dwarf galaxies today, and many of them then can merge, accumulate into bigger galaxies of Hubble sequence. But these will be, in some sense, primordial building blocks, because if you do something to a dwarf galaxy, it's gone. So they can be gobbled up by bigger galaxies, and that happens all the time. And they come in at least two flavors, gas poor and gas rich. We may be transitioning from one to the other, but they're by far most numerous galaxies in the universe. But they don't contribute the bulk of the stellar mass or star formation.